one topic that was put in two-dimensional waves for reasons I don't fully understand is the idea of a phase difference. Now, this is something that right now is going to just seem kind of mathematical, and that's really all it's going to be right now. However, later we're going to need this if we want to talk about interference, which is really important for thinking about diffraction, for instance. So mathematically, this might not seem very juicy or very helpful right now, but later this is going to be hugely important. So when I say phase, what I actually am thinking about doing is simplifying the argument of my sine wave, right? So if you think about a sine wave, you can kind of start here and go here and talk about this as going from 0 to 2 pi, right? Sine of an angle effectively goes between 0 and 2 pi. Now, if you're paying attention, you might notice that I actually started it at the wrong spot, right? Because technically, it should go up first if it's a sine wave. So a better way would be to call this pi, call this 2 pi, and call this 0, right? That's what a sine wave looks like. This is 0, this is pi over 2, this is pi, this is 3 pi over 2, and then 2 pi, okay? So when we talk about phase, that's what we mean. Where are we on the sine curve? Now, we can talk about phase difference. Now, this is either going to be between two waves or 2 points on the same wave, but that's kind of just the same thing. So phase difference, we need to construct a phi. And one thing to be careful of is that this was our initial condition, right? This just tells us our where we start at x equals 0 and t equals 0. So be careful to recognize that we're using this Greek letter phi in two different places to mean two different things. This is just some constant. So I can plug in a specific time, right? Notice that this is a snapshot graph, which means this needs to be at one moment in time. So this moment in time comes in there, and that maybe has a value, 2 seconds, whatever it is. But then we can look at different positions, right? Our x2 and our x1, and we see that where our dot is on the curve is quite different. So again, if somewhere over here is our 0, and this was 2 pi, this point here is a little after pi over 2, right? So this isn't 0.5 pi, this is, I don't know, maybe 0.55 pi. When I look over here, this is even after 2 pi, so I could think about this as actually starting again and being 0, and then at this case this is a little more than pi, but not yet all the way here. So maybe this is 1.2 pi, again because I've restarted at this point. So the idea being that I can then have a phase difference, and you can actually re-express it this way. Now, if you do express it this way, you can have a greater than 2 pi. So this would be like 2 pi plus 1.2 pi. And as long as you just take your delta x and express it in terms of wavelength, what fraction of a wavelength is it, this will work out. And when I say fraction, again, it could be greater than 1 wavelength, as is the case up here. So the reason we're going to talk about it that way is, again, when we think about interference. So mathematically, all we're trying to do is say, where are we on the sine curve? Thinking about it as just sine theta, but then we can think about in time and space, where are we on the sine curve, and then think about adding these together. So this is going to be helpful when we start adding together waves, which is necessary when we do interference.